In education, research, and professional development, it is common to observe that highly intelligent individuals sometimes underperform in certain subjects. And this raises the important question, why doesn't intelligence guarantee high performance? And there are three interconnected psychological and cognitive factors that explain this phenomenon. They might not be the only ones, but these are actually very important factors that we will consider in this lecture. Intelligence is the first one that we will indicate with the letter I, especially this will be useful when we consider a mathematical model, a simple mathematical model where we indicate the intelligence level by the letter I. Then we have interest, or if you want, subject interest, that we will indicate with the letter S. And by interest, I mean the degree to which a person finds a subject inherently engaging, meaningful, or rewarding. And then we have another factor that we will consider, which is motivation, and we will indicate it with the letter M. And as you can understand, motivation is the internal drive to act, which is shaped by emotion, even hormones like dopamine, serotonin, cortisol, and even other possible hormones. For example, in the human body, especially when we consider males or men, we have testosterone. So also those hormones which are related to sexual hormones are actually also indirectly or even directly related to our motivation level. And then we might also have habits, mental health, and environment, which in some kind of intertwined actions, they affect our own motivation level. So this is what we will mean by motivation, more or less. So I don't want to be extremely precise while considering these topics, but I want to give you the key idea, the core idea. And the key idea is that performance is not determined by intelligence alone. Interest and motivation act as multipliers. I will tell you what I mean by multipliers in some later slides. And these multipliers amplify or suppress the expression of intelligence. Now, this slide is titled Interest as a Cognitive Amplifier. And in particular, interest shapes the following aspects like sustained attention. So, if we are interested in something, chances are that we will keep our attention to the best possible degree so that we try to retain as much as possible the topics that we are learning. So that's the idea. And then we have some kind of long-term memory consolidation because if we are interested, chances are that it's going to be harder for us to forget about things because we are really interested in them. And for example, I can speak personally, this occurs to me very often. If I'm not interested in something, I might forget. Um, and sometimes, for example, when you meet some people, you have a large group of people and you shake hands with several people and you introduce yourself and those people introduce themselves and they tell you their names. And even if you try very hard, sometimes it's very hard to remember uh, all people's names because there are some aspects related to the fact that you are not paying attention to their names because maybe you are focusing your attention on the way you should behave towards those people and so on. Some other times you might just not be interested, and there are several intertwined factors that will contribute to your forgetting those people's names. And this is just a simple and even stupid example if you want. But interest has a lot to do with memory consolidation, not just in the simple example that I gave you, but in many other examples. And then, of course, even the willingness to explore things, because if you are interested, you want to know more and more about a certain topic, and then you have more tolerance for frustration. It means that even if you are not understanding some concepts, still, if you are interested, you will be tolerant because you maybe you can be a little frustrated by the fact that you don't understand, but thanks to this interest that you have, you will be tolerant towards the frustration that you feel in some specific moments. And then another important point might be an intrinsic effort which you make to understand things that you are interested in. So these are just some aspects. I don't want to pretend or act as if they cover everything. These are just some points that I wanted to pinpoint, to highlight, and it's just some of them, not all of them. And then, if a subject does not spark curiosity, even a very intelligent individual will allocate minimal cognitive resources to it. So this is the important part of this slide. And then this slide is titled Motivation as an Energetic Driver. So motivation governs how quickly a person initiates tasks, how consistently they persist, how they handle setbacks, the intensity of their engagement, and as we said earlier, hormonal and psychological factors strongly affect motivation. So low dopamine might lead to difficulty initiating actions. High cortisol, which is related to chronic stress, might lead to avoidance, fatigue, and depression, which is a very widespread epidemic, if you want, quote unquote, epidemic in our modern day society. This leads to reduced reward responsiveness. So, depression, of course, has several different layers in which it's going to affect our bodies. But one of them is definitely the fact that you have some reduced reward responsiveness. So, if there is something positive that's occurring to you, you don't really have the strength, the mental strength, and also the physical strength to react to that. So, to appreciate something positive that is happening. But actually, you are more inclined to see things negatively. And that's the problem of depression. One of the problems of depression is that you're going to see things with a nuance, with a negative nuance, and you are going to slowly react to what's around you. And even if it is something positive, you might not react like a normal feeling person would react. Then there is also a multiplicative effect that I mentioned earlier. So I want to explain what I mean by multiplicative effect. So if interest or motivation is near zero, performance will collapse regardless of intelligence. And this explains why talented students may fail in unappealing subjects, or depressed or chronically stressed individuals underperform. And also, interest driven learning often dramatically outperforms forced learning. And this multiplicative effect is going to be seen in this law that we are going to consider. So here I'm considering a function, p of t, which is given by the product of some quantities. So first we have p max, and p max is a maximal attainable performance. So it is just a scalar where p of t is the performance at time t, let's say. P max is the maximal attainable performance. So we want to construct a simple mathematical model. This will be the first equation that we will consider. Then we will have another one that I will show you in a moment. But first I need to explain what this is. And then I here is the intelligence, as we saw earlier in previous slides. Alpha, beta, and gamma are simply uh, model sensitivity parameters. They are exponents and they model the sensitivity. For example, if alpha is large enough, then the intelligence here, the level of intelligence will be more and more important with respect to the other two. S, as we saw earlier, is the subject interest, so the interest in a particular subject. And beta is its model sensitivity, its sensitivity, let's say. M of t is motivation, and in this model that we are going to consider, motivation is a function of time. So I and S in our model will be fixed, even though later I will show you what happens if I and S change. So we can consider some implementations of this model where we can gain some understanding even if I and S change. So in this specific example, M is a function of time, whereas the other two are not directly related to time, so they are not a function of time. Then here we have a dynamic variable, which is M. So we are going to consider a dynamic equation. A dynamic equation tells us how motivation evolves over time. So dm over dt is the derivative, or if you want, the rate of change of motivation with respect to time. And in our model, this is equal to minus lambda. Lambda is a positive constant, which we can call repulsive factor, if you want, which tells us that M tends to go back to its original base state, let's say. So M0 in particular is baseline motivation. And the fact that there is a minus sign here, it tells us that the rate of change is negatively affected by this. So if M is greater than M0, this part here is negative because lambda is positive, is assumed to be positive, and therefore this rate of change would be negative because of that. So it also depends on these other additional terms, of course, but if we just consider this initial term, this negatively affects dm over dt if m is greater than m0. So it's like a part of the equation which tells us that the rate of change tends to go towards the baseline motivation. So that's the intuition. But of course, we also have other effects that we need to take into account. And the other effects are the fact that we have some reward feedback, which we call R of t. And this might also be proportional to performance, if you want, in some cases. In this case, we are not considering a direct relationship with performance. And eta is just its proportionality coefficient. So if you want eta, if eta is large, then we have high sensitivity to a positive reward, if you want. So this is a positive term because if we are rewarded, maybe our motivation, so it's definitely possible to think that our motivation levels will increase due to our reward, which can be different types of reward. They can be monetary rewards, so we can be given money to do some certain things, if you want, or we might be rewarded because if we I don't know study a certain topic, then we might be able to pass an exam, or we might be able to find a job, and so on. That's the idea. And then we have another negative term with a minus. So we are assuming that these constants here are positive. Then we have this negative term, which is proportional to d of t. And d of t is the level of stress or depression load, if you want. So it is linked to depression, and therefore this has a negative effect on the rate of change of our motivation. So it will decrease our motivation. It tends to decrease our motivation. And finally, there is also some random noise proportional to xi of t. So we have some parameters eta, phi, and sigma, which explain for the sensitivity that we have towards rewards, stress or depression, and noise. So this is just some random noise that we will model using a normally distributed random variable. So a Gaussian distribution will be the distribution of this random variable xi of t. And this simple equation captures homeostasis, for example, which is the return to baseline, and it is explained by this initial part, the baseline motivation, which is related to baseline motivation. And then we have some reward-based reinforcement, thanks to R of t, and then some negative effects of stress depression and random motivational fluctuations, which are common in real life. And by the way, I also want to add the fact that in this previous equation here, which is this multiplicative equation, you can see that we multiply these variables, I, S, and M. And why do we multiply them instead of adding them? Well, my explanation is this. For example, if you are not motivated at all, so if your motivation is zero, well, it's quite simple and logical to think that your performance, P of t, will also be highly negatively affected. So it must be zero or near zero. If your motivation is zero, we can assume that our performance will be zero. On the other hand, if we simply add these terms, well, we basically separate the parameters. So even if we have zero motivation, we might have a high performance because they are separated in a sum, and it's as if we are considering them as independent in some sense. So they are separated. Or, for example, even if we have very low intelligence, then we might still have a high performance, which to some degree it is still actually possible. Of course, even if we have a low intelligence, we can still high perform because we are highly motivated. Maybe it's easier to think that if we have very low motivation, we underperform even if we are intelligent. So you might try to find your own model. So this is just a simplification model. It is just a simple model to show you some aspects that you can consider when you construct such models. But anyway, this is the model that we are going to consider. So we multiply these terms. And for example, if we have low subject interest, then the performance will be low because of this multiplication. Okay, so this is the first equation, and then we have this other equation, the motivation dynamics. So at this point, we are ready to switch to MATLAB, where I simply implemented this equation together with this one by choosing some parameters, and then we will do some simulations quite quickly, so without wasting too much time. Here I have prepared my MATLAB script. So I define the parameters that you saw earlier. I will not get into the details of these parameters. I have chosen some parameters. Then in here, I implement the multiplicative performance model. So I have performance equal to the maximum possible performance multiplied by I to the alpha times S to the beta times M to the gamma. And then I also, of course, do some other simulations which consider also the dynamic part. So here I implement the dynamic part. In particular, I have minus lambda, so I have dm over dt equal to minus lambda times m minus m0 plus eta times r minus phi times d plus sigma times, and here I have this definition here, which is not exactly as in here. Where is it? You remember that here we have sigma times xi, but in here I have sigma times the square root of dt, where dt is the increment in time, times this rand n. So let me explain. Rand n is a normally distributed variable, which is generated by MATLAB quite randomly, let's say. And it is multiplied by the square root of dt due to the properties of the so-called Brownian motion. So this is related to Brownian motion, which is also related to a Gaussian distribution, or if you want, a normal distribution. If you know the Brownian motion, you might understand that, but of course, this is not the adequate video to explain Brownian motion. I have explained it on other occasions. It's not the video in which I would like to dig deeper into Brownian motion, because it's not the point. The square root of dt, let me just say that it appears because, for example, when you consider Brownian motion and you consider the motion of particles, or you might even consider the evolution of prices, whatever, but you are considering Brownian motion, just like the one that Einstein considered in his famous articles in 1905. It's something that dates back to a very long time ago. It's very well known. It's a very well known process. And if you consider, for example, a particle, a system of particles, and you take the average of the displacement of the particles, you get something that is proportional to the square root of dt, to the square root of time. So the square root of this dt here represents the standard deviation of the process. To simulate a Brownian increment, we generate a random normal variable with zero mean and variance equal to 1. Multiplying by the square root of dt, the variance becomes equal to dt. Okay, and that's the point of the Brownian motion. It's something related to the properties of Brownian motion. So this preserves the defining property of the Brownian motion. But as I said, this is not really the point of the video. The point of the video is to show you the simulation of the model. And here, by using, for example, this equation, it's like integrating. We are inside a force cycle here. So by summing over t, we are basically integrating over, we are integrating this dm over dt, and we are building m of t. So we are constructing this m of t, so we are finding m of t from the differential equation. That's the idea. And then we can also, of course, calculate p of t, so the instantaneous performance in this multiplicative model. So once we find m, we can also find p, because s and I are supposed to be fixed. And I have created some graphs, some plots. I will not explain all the parts in this script. So let me run it. I have generated basically three graphs. Let me go to the first one. So in the first one, we are considering a three-dimensional graph. For example, let's consider this one on the left. In this one on the left, we have m equal to 0.2. So remember, that's the motivation level. Whereas on the plane here, we have intelligence and subject interest, or just interest. The point of this graph is to show you that while we move to the right, the motivation level increases simply because we are creating the same graph by changing m. The point here is to show you that the more intense colors, which are towards the yellow color, are found when the interest, the intelligence, and also the motivation are at their maximum level. So for example, here in the third graph on the right, the color is more intense because you can see that there is this 90 here, and it's at the tip of this kind of triangle where the interest, intelligence, and also M are at their highest levels, basically. So we can close this one. Let's check this other one. So in this one, we have the plot of motivation with respect to time. And in this case, according to the parameters that we have chosen, you can see that there is a decrease in motivation as a function of time. And below, you can see that performance will also be negatively affected if motivation decreases over time. You can see that performance also decreases over time. And this is quite easy to think about because performance is a multiplication of the parameters that you saw earlier. So if motivation is low, performance will also be low. That's the intuition. So this is a simple graph. And we have a final graph here that's quite interesting. In particular, we have three curves, a blue one, a red one, and an orange one. In the blue one, we have s equal to 0.1. So we are changing s in the three curves. So the blue one is where s is the lowest. And remember that s is the interest level. So you can see that the performance will decrease over time when the interest is so low. On the other hand, if the interest is a little bit more, so it's more than 0.1, in this case in the red one we have 0.4, you can still see that it decreases. I mean, the performance decreases, but it's a little higher than the blue curve because interest is higher. On the other hand, you can see the interesting effect that we have in the orange curve because interest in this case is quite high. And by the way, these are normalized values. So interest is a value between 0 and 1. We have to choose a normalized value between 0 and 1. So it means that when s is 0, we have no interest. And when s is equal to 1, we have the highest possible interest. So 0.8 is quite high, very high because it is close to 1. And you can see that as time increases, the performance increases. And it really reaches high values in this case. So the orange curve showcases an increasing effect due to interest, whereas in the blue curve and the red curve, we have a decreasing effect due to the low levels of interest. So these are just some aspects that I wanted to show you from a very simple model. And with this last simulation, I would say that I showed you what I wanted to show. Therefore, we can say that the video is over. Thank you for your attention.